Yeah, so our talk is called Linux and Windows Perf Analysis using WPA. You see WPA is crossed out there as kind of a half joke because WPA stands for Windows Performance Analyzer, and obviously this is Windows, so we'll work on the name. Just a quick poll, first the easy one, like how many people use LTTNG today? Going pretty well. All right, awesome. How about WPA? Have you heard of it? Hands? No, that's decent. Actually use it? All right, got a couple. He's not a plant, by the way, so that's awesome. So anyways, my name is Ivan Berg. I'm a dev and perf analyst with Microsoft.
Yeah, my name is Tristan Gibeau. I actually work on WPA and some of the infrastructure processing traces as well as collecting it for Microsoft. And yeah, just been part of the ecosystem for helping performance across Windows and now for Linux and a few other operating systems for about the last 6 to 8 years.
Cool. Yeah, and a special shout out to Nicholas, who's also worked on the plugin. He's in Vancouver, he couldn't be with us today. All three of us are in the Microsoft Cloud and AI division, CoreOS group, so we support Windows and Linux as well. And we are also in the fundamentals group, so we do kind of the debugging tools, UTW, tracing, all that stuff. So I know all of you guys care about debugging and getting deep into what makes any system tick, so that's a special love for us. So whatever works there.
So for our agenda today, we're just going to go over a little bit of history. You probably were wondering, like, okay, how does Windows do its instrumentation? Figured to kind of give you like a little bit, like a 401 on that, how it works, and not go too much into it. But also why we are actually tackling this, why we are, because Microsoft does love Linux. But why has this become a thing for us, and why we are starting to do investigations on performance for Linux, as well as Internet of Things and other operating systems. And then kind of talk about the different tracing types that we're using. We're going to do a live demo of our WPA SDK, and we're also going to go over some final thoughts. So for short history-wise, ETW stands for Rent Tracing for Windows. I know. Very, very thought through on that name, but it's been around since the Windows 2000 days. It's both a kernel and user instrumentation platform for Windows, so you write it once, and depending on where you are, you can write it for kernel drivers, for the kernel itself, or for a user application. It's built into the kernel. We do sideload, we have a user space area too, but it's part of an inbox component. It is pretty performant, at least to what we use it for. There's some folks that can argue that, but it's been working pretty well. And we use it mostly for a combination of real-time and memory-backed tracing. The biggest thing we use it for is for production analysis, so we actually do off-box processing. We try to, at most, not actually affect the machine when we're actually doing the performance tracing, because that wouldn't be very useful. There are a few folks that also use it for real-time from a combination of different things. And there's really two big modes for it, global and in-process capture. In-process capture is more of a recent thing, so that people can do capture within their application. So this way you don't want to get access to certain events. And then, just real quick, the Windows Performance Analyzer, WPA. It's been around for quite some time. It actually started as a command line tool back in, early '95, and it kind of evolved to simple tables, and then eventually turned into timeline graph views. And now, to kind of give you an idea, this is kind of like the ecosystem that a lot of Microsoft developers have gotten into. And we actually have the next slide. So you might be asking yourself, why do we update WPA to understand Linux tracing? Well, me and probably about 1,500 other performance analysts inside Microsoft that looks at tracing for Windows started to have to learn a little bit how to actually do tracing for Linux and how to analyze that. And they started using Trace Compass. A few folks started using Babel Trace and Babel Trace 2.0, but a lot of them were like having that hurdle for trying to understand how to use these different tools. So we decided to jump in and try to help out by making a tool that they use for analyzing performance of Windows to make it understand performance traces for Linux. And we have a big community, both internally and externally. We actually have a few folks in Google that actually blog about us. They're our unofficial documentation, more or less, because we do a great job of documenting all of our tools, but they do an even better job. So we kind of wanted to try to, enlighten some of these things, especially with a lot of the stuff that Google's been trying to do cross-platform. We try to make it better overall. Other than that, we try to find, the biggest thing we try to find is no problem can hide, because we have gotten into that needle in the haystack part when there's something that is a small failure point at a low level service, and we're, from especially in Azure environments where we have multiple services working with each other, that we need to be able to actually do heavy diagnostics to actually go and see exactly why, a thread was preempted or something was happening on the actual box.
Yeah, perfect. I really like that no problem can hide. That's why NTW and the equivalent for Linux LTTNG has been quite successful. There's lots of different perf tools, but being able to take a trace and be able to peer inside is pretty awesome. So in case you haven't used WPA, we'll do a live demo soon, but this is just a screenshot of the live demo loading LTTNG traces. We have a bunch of views which I'll present in detail, but just real quick, just a couple of views. So first just an overview. So first on the left is this whole, excuse my bad drawing, graphs, live graphs of what's happening on the table on the right, and you can either double click them or drag them to the right, and then you get a lot of graphing abilities for WPA. And you can change, in any of these views, you can change a lot of the graphs and the data. A big key feature is you can drag multiple graphs and zoom in and out on the timelines, and get a lot of features you'll see in the demo. Two other things, we won't go into huge detail, but it's a pretty key feature, is that here there's something called gold bar. So it's basically grouping on steroids, like SQL or Excel pivot tables, where you can drag these and get groupings and stats and stuff on the fly. And then on the right is the blue bar where you can graph anything. So there's a lot of pre-canned views which you want to use because to show you different views of the system, but you can also have WPA configurable to kind of graph whatever you want, essentially, whatever data you want. So that's a quick overview of WPA if you haven't seen it. Again, there's lots of diverse tracing tools. They all have their use purpose. I love all of them. Just a real quick recap though, the reason we picked LTTNG usefully is we think it works really well for an offline system level tracing, which is great, so no problem can hide. Offline is mostly true with a little bit of asterisk. There's a couple points we think we can clear up, but also this type of tracing works well for large scale data collection and analysis. So I used to work on both the debugger scale analysis and tracing scale analysis, and internal insiders and people can opt in and process 500,000 traces a day, for example. So having it be programmatic and system where no problem can hide is awesome. One of the challenges with system level tracing, the pros is it's system level, so no problem can hide. The cons is it's everything, it's the whole system. So it can be overwhelming, challenging. So that's where you want to sift through a large amount of data, right? This is where you have 100,000 events, you have 1 million events that you want to aggregate, you want to get stats on. So you need good tooling. So actually the same diagram that I showed before, just a little about the tracing categories. Again, at the bottom we're talking about LTT and Perf. The spiritual equivalent is ETW, and that goes up and down the stack. And then there's other ones, targeted perf tools, which generally look at one subsystem or another. And then of course we have UPPF, or custom system observability, which is pretty awesome. Plug XUD traces available on Windows now, publicly and open source in the last couple months. So if you use Windows, that's a thing as well now too. All right.
So we've been showing off WPA, which is a Windows-based application coming from a perspective of a bunch of Windows developers. Well, one of the first things you wanted to do before trying to enlighten up Linux support for trace processing and be able to consume certain types of logging file formats other than common trace format or CTF through LTTNG, we decided that, we're going to build a brand new framework for this, and we're going to build it on .NET Core. This way we can make sure it can be cross-platform, and we can make it open source. That this way we can share the learnings that we've brought in from different things. And this is kind of just giving you a quick overview of how SDK works. This is a very, very high overview, but ultimately it gives us the ability to have multiple different streams come in, and these streams allow us to have different event processors. Now the idea is that it's all composable, so you can have a processor depend on a processor, which depends on another stream that comes from another processor. It probably sounds a little bit like Babel Trace 2.0. It's kind of the similar ideas. We all kind of are rehashing the same thing over and over again. That's why we're trying to make it open source. One of the things we're also working on too is we have, TO projectors is a thing that, WPA is a very tabular-based UI and has a lot of views, but we started adapting it to make sure that we can actually build other views, whether it's web-based or some other tool wants to consume like Trace Compass or something like that. We can actually feed this data in for someone that's already built out tables and things. A sample, for example, for how we do the common trace format is it's simple. We have a set of CTF streams, whether it's file-backed or directory-backed. We do some tricks around that. The event parser playback is ultimately a way for it to register based off certain events. In this case, that can be like my event. It processes that event payload and generates some type of state. Or if you want to, you can register one or many events or all events to get something like a generic events type table. Kind of a very high level pseudocode. Don't read, it might be some interesting errors in these. It's just simple, like you have a process async that is all C#ified that gives you the ability to have file pass. You pass each one of those entries. In this case, we have a text file that has a bunch of log entries. You pass that off to a set of data processors, which will then go ahead and whoever's consuming it, it'll set up the dependency stack and the dependency queue as far as like how many passes you may need to go over the trace. Say, for example, you're trying to read a 45 gigabyte trace and you want to allocate your memory the first time around instead of doing it dynamically to help improve performance. You could do that, but you can also then correlate data across multiple different data points. So if you want to do something from a text file to a CTF file to an ETL file and be able to combine that information together to actually build a new table that takes all of that data points. And on the right-hand side, we have a simple table builder. It's designed that you actually query outputs based off of what the extensibility endpoint is. The extensibility endpoints can be anything from generic strings to very complex structures with lists. We do some stuff under the covers because memory allocations and managed heap can be fun. So we actually try to reduce the overhead as much as possible at the engine layer. So this way you're not using up as much memory as possible. We've learned the hard things, processing Windows traces that can be very large.
And one thing real quick on this too, that is not clear, they're separated also because you can access the data and all the correlation and stuff the plugins do programmatically and have it separate than the UI.
Yeah.
So they're separated but for a reason as well.
Yeah, you can separate these out into completely different binaries or be in one Uber binary if you want to.
Cool. So we'll talk about the plugins with the new SDK that we're currently supporting for Linux. So of course we have LTDNG, system level tracing with the SDK. We've also wanted to correlate with other logs, so these logs like dmessage. There's other couple logs you may or may not have heard of. First is CloudNet. That's an open source set provisioning type of tool that runs on a lot of different cloud vendors that provisions any VM. So another one that's Microsoft only is YAgent. So these get logged just as text-based logs. And we want to correlate them with LTDNG. They're always logged to the disk, and we want to see, hey, if there's an action that's taking, what was the user space action and what happened. So again, we want to analyze the offline traces. We want to provide these type of views, threads and processes, context switches and CPU usage, syscalls, file events, block I/O, and disk activity, and then diagnostic messages. One key thing about the plugin is that it's not just looking at the raw events. We've tried as much as possible, although it's early days, but we're trying to do a lot of secondary processing and correlation that you'll see when we do the live demo. So for example, for a syscall, you get the entry and the exit for the syscall. Well, obviously you want to know how long the syscall took and graph it and all this stuff. So we're actually correlating those when we can. The same thing with disk and file I/O. And then all that data should be available programmatically. But then we hopefully can graph all that rich information as well. And kind of where we're coming from in Windows, as you'll see me talk about it, is we're kind of used to certain things in Windows. And so if the raw data is not available, we'll say, hey, why isn't that there? And usually you can calculate that somehow. There might be some other things which are just like this far away from us from LTTNG having, which that hopefully we can work with the community, and we'll talk about at the end to add that support. All right, so we'll do the live demo in a second. Just as a quick setup, I'm not going to record the trace. Most of this should be pretty familiar if you're used to LTTNG. I'll just call out a couple things that I thought were interesting. First, like this star support, which is kind of useful, so you don't have to have a huge giant command line. We're enabling syscalls here. We're adding context optional fields, which help with the correlation. So these are, you don't actually have to have these or the state dump, but it actually, our correlation is better because of it. And then we found, for one reason or another, even though we're enabling state dump events, we found that we've had to issue this regenerate state dump right before we stop it to get the rundown that we wanted. We call it rundown, so which is like being able to map disk names and processes that started before the trace and all that sort of stuff. So open to feedback at the end. It's like, hey, we can add this or whatnot, but this is the specific type of tracing we took for the demo. And then I have two demos. First of all is Linux VM. This is going to show multiple plugin support with the SDK. So this is correlating multiple different plugins and showing them. And then demo 2, you'll see that we used StressNG, which is an open source tool, and just ran 3 different scenarios. First doing stress on the CPU, second doing stress on block IO devices, and then third one just hammering the system with syscalls and file system related operations. Okay, so again, I wasn't going to bore you with the internals of WPA, so hopefully you can kind of get some of this. And I'm going to kind of start easier and then go a little bit deeper. So I have a graph I've already loaded here, which happens to be disk activity. And mostly I have this demo just to show the basic UI and the correlation. So latency is a big thing if you're into this. And so we see that there's a spike in latency at second and a half IO times in this period. And so one common thing we want to do is be able to kind of investigate what happened during that time period. In this particular case, this is a VM that's coming up, and I mentioned that we want to do correlation between other logs. So I have this plugin just open all the logs, including LTTNG, and it'll just go and parse them. So another table that we want is cloud init. So you see these events are around the same time period. So let's go zoom in on this spike. And so there we are. So it'll become clear in a second, but it actually shows up pretty well. It doesn't always show up in all presentations, depending on the blue light. And you see when I highlight something, it highlights it in blue, which is kind of a key feature just to show you where things are happening. So we're graphing latency. So one of the things we're calculating here is IO time between when block IO request gets inserted and completed. So you see here you have, this is both the aggregate and the individual IOs here. And so we're starting to see at the very end, there's a second and a half spike, and the average IO time during this period is 409 milliseconds. Not great, but there's one IO that's actually second and a half max. And you can go in here, and for example, you can sort on max, which I believe it is already, and you can drill into these. You can actually, let's say, just click, and it'll highlight which IO that is, the max IO, okay? So again, in the highlighting bit here, so let's see, I just happen to kind of know that in this case, this is a VM coming up, and this is temporary disk being formatted, and depending on the configuration of the VM is how many IOPS and throughput you get. So let's just see what happens in this time period. And so you're seeing stuff for 6 seconds duration. And one of the things about WPA is I can kind of scroll down here, just look for anything blue, and I can see that these events are highlighted, and I can see, hey, guess what? We're actually formatting the disk, creating the file system, and you see the cursor is moving here. So now I'm in the middle of the format, then I throw in some latency, and then finally at the very end here, you see the little blue line jumps, and it said, hey, the format took 2.229 seconds. And so So you're getting timelines between different graphs here. Another thing you're getting is you're getting UTC time, which you get with all these logs, but you're also getting relative time, so which is kind of cool. You get that for free with the WPA. So in this case, we started LTTNG up as early as possible in the Linux kernel. It starts like a little bit before user space. It's tracing, and then Python, a bunch of other libraries load, and Cloud starts to activate. So in other words, they're in different timelines. And what we're doing is, however many logs you're opening is actually figuring out where they overlap. And this relative time period, it's calculating that automatically. So that's kind of nice. So you don't really have to think about it, because remember, when I was analyzing these logs, kind of in the text format, you would get timestamp formats and all that stuff, and you'd have to calculate it in your head, and just is not so much fun. So that's the first demo, kind of showing the unified view, not really drilling into anything specific with the views, and then I'll move to the second demo. Okay, so the second demo I mentioned it was stress load applied. So right up here, you see there's 4 analysis tabs: overview, stress CPU, block IO, and syscalls. A little bit cheating because I know I ran these beforehand. You'll see, even if you didn't know what was going on in the system, you would be able to tell quickly. So imagine you had no idea what was going on in the system. The whole point of these tools is to be able to figure out what they are. So one of the things with any tool you probably want to take a look at is CPU utilization. Obviously, you can be blocked on disk and network and other things, but it gives you an overview of what's going on. So you see, this is a 2 CPU VM. We're graphing CPU, so this will dynamically update, and you see it's highlighted in blue, so one of the features of WPA. So if I click in here, it will highlight all the data points. And so we can quickly see that there's 3 sections here. We're running these commands, and if I just, for example, just highlight this one section, you see in this thread's history, which is a view we've come up with, you can see that we're running sudo stressng during this time period. If I pick the second time period here and scroll down, there's another set of stressng commands, and there'll be a third as well. So it would also be awesome, I kind of mentioned this in one of the side talks, is like, it'd be really awesome to know the arguments to these commands as well as a user. You just kind of want to know, just like with strace, what specifically arguments we pass to, just like I showed in the slide. So I have some of these views preloaded, so let me move over to stress CPU. So first of all, we have the same view, but we're going to do the zooming behavior to kind of zoom in one region here. Okay. So you might have barely noticed that the CPU usage is updating automatically to show that together we're using almost 89% of the CPU, and so this is both aggregate and individual events. So these are actually individual context-switch events, and so you see the new thread that's running is stressed at the GCPU, and it's in a running state. So most of this stuff is kind of the raw data, I would say. So you know that something's running on the CPU, and the specific command that's doing it. And I believe the command isn't available in terms of the data. We're actually doing correlation between other events. And then, so that is the first view of context, which is utilization by CPU. So let me move to a couple of other views. First of all, which is utilization by process thread and timeline. So this is actually the same data, but graphed in a different format, and they're in preset views. So again, you can configure WPA however you want, but these are helpful for getting different views. So this is sorted by CPU usage again, but this tells us any specific thread, which thread is hogging the most CPU during this time period. So if I expand this, we know specifically that this thread ID 2867 is the one that's consuming the most of all the threads. And if you highlight it, you should see pretty much blue across the whole timeline, which makes sense because it's the heavy CPU hog. And what else? And then you can look at it per CPU basis and look. Hey, you see that I believe 2867 and 2889 are some of the biggest hogs here. Another thing we do. So apparently the Linux kernel doesn't actually differentiate between everything's in the running state, even if it's blocked and not able to run on the CPU, or it's actually running on the CPU. But because we're looking at context switches. and we actually know how often things are running. We can actually take a look at one of these threads, like 2865, one of these threads right here. We can highlight it, and then we're actually producing stats for how long it's actually executing. It's ready, it's running, it's sleeping, or just sleeping, or waiting in general, which is the combination of sleeping and just sleeping. Now, if this were Windows, we obviously want to know what's running on the CPU, like which programs running on the CPU, but actually which functions are executing. So I'll just do a quick call out, and I'll make several of these comments during the presentation. There's another graph that you get on Windows called CPU sampling, which you'll be able to actually see, hey, the processor is actually executing this specific stress ng code. And I'd love to get that on Linux. It sounds like we're very close to being able to have that. That's CPU clock events that Perf will collect. And so if you had that, you get another view, not only what is the processor switching, is it being blocked, preempted, all that stuff. We'd also know specifically what inside stress ng is doing, which would be, I think you'll agree, would be awesome to have. You can get that with Perf today. So the second one is block I/O. I also will do the same trick here and zoom into the region that's of interest. You also notice on the left the views are updating automatically, and so when we're looking at individual events here, you notice that there's actually less CPU usage in general, but also it's a different command, stress ng HDD, but also the threads previously state was sleeping a lot, which makes sense because we're doing block I/O. And because we're doing these calculations like I/O time, we have some pretty cool graphs. If you work on disks, you probably know IOPS and throughput are some key features and characteristics of a disk that we advertise. So, hey, let's look at, let's say I/O latencies over time. So similar to it actually is the same graph as before, but we can see that we had this, we're graphing average latency, 210, during this time period, so that makes sense. We had a time where no I/O, well, apparently no I/O was issued. We can just visually quickly see that, hey, on average, we're doing 200 milliseconds. We have one I/O time of 400, and if we wanted to, we could use the same trick that we did before and just like sort on max, and it'll tell us exactly which I/O took the longest, which is pretty cool. And then in parallel with that, just a different view, same data, is like outstanding IOs over time. So this means like, hey, it was inserted in the queue, but it wasn't completed. So that's basically, you can just accumulate IOs, and sometimes the graphs will look similar, but you use them hand in hand with IO latency. So it's average IO latency is taking n number of milliseconds for an IO request to be serviced, but also like how many IOs are in this queue, right? And so let's graph that, right? And you see some of this like stair-step behavior here where like, where they're just building up and then they get serviced and it spins down. Also, you might want to look at what your actual IOPS are for this time period and see if that matches, like, well, for example, if you're running this on your local machine and you have an SSD and it said advertises 40,000 IOPS, like how many IOPS are you actually getting? Now, obviously that's there's a variety of factors that go into that, your I/O size and all these other characteristics, your load and whatnot. You also want to look at your throughput, so how many megabytes per second is coming through. So we just look at individual IOs. Max IO size was 5 megabytes, but we can see how many bytes per second or megabytes per second we're pushing and graph all of that. So it's pretty useful. Okay, so the third view, again, I ran stress with the syscall stress. I'm going to zoom in for this last region, and you can already see it's pretty CPU intensive. I got the top one sorted, so thankfully it's actually running commands we can see, so that's running stress ng change directory. So we have this disk IO activity. It's actually block IO disk IO activity. One of the things we try to do, there's some challenges with it, but it's to correlate disk IO and file IO if you can. And so like one of the things, for example, this is something we have on Windows, and it's pretty foolproof, I would say. Well, not every file system call results in disk IO, and there could be disk IO that's not file system. But what I mean is when you actually make a file system call that results in IO, the trace ETW will trace that for you and display it. So we're trying to do something similar here. Like if you, for example, in straced, if you, you saw an open and a write or a certain file descriptor that resulted in an I/O, you'd like to be able to know that those two things are correlated. So one of the things so for example here, you see I am sorting by device and device name here and clicking on file path, and you see the little blue line is perfectly aligned with the start of my CPU usage on stress ng change directory. So it just kind of gives extra confidence that, hey, really like this I/O happened just as I was running the change directory. And you can do, this is the same disk activity from the previous tab, so you can do all the same sort of stuff we just did. But we probably want to dig into syscall latency. So we actually have all syscalls, and we actually have a modified enhanced file events, which is a breakdown of all syscall related file events and parsing them more specifically. But so with the aggregation capabilities with WPA, so we can just see we're sorting by count here. I don't know if you guys, can you guys see that pretty well? It's very small. Okay, let me zoom. You guys just shout out if it's too small here. So the user, you can go in and sort, and I'll do that in a second, but you see syscall count operations are here. So this stress test did its job, and it's producing in a short period of time. Here, with 3 seconds, 158,000 change directory syscalls. And so if you click on this here, it'll highlight the same time period where these are. And you can see like the average duration. So this is in seconds. Let me just change it to milliseconds real quick, which is a little bit more human readable. And I'll zoom in here. So you see the average duration is way less than 1 millisecond. We have a syscall change directory that's 96 milliseconds, which sounds pretty bad for a change directory. Sort by this, for example, by max duration here. And we'll actually show you the arguments to that syscall and where it is. So typically, it's probably not change. I'm just guessing. I'll guess here that's probably not change directory's fault. That it took 96 milliseconds, but probably because of the load on the system, so you can correlate with the other data and what's going on. So the last view I'll show you is the file view. So I just double click on that and it's going to load here. And we try to have, I guess, more, everything in this view is from syscalls, but we're trying to do more parsing and provide you, I guess, just more data, how long the duration of the file system calls are. I think that's it for the live demo. Thankfully it went okay. You guys can be the judge of that. So yeah, final thoughts. We were really open to ideas and comments from the community. We plan on open sourcing LTDNG and those plugins hopefully in a couple months. There's a link where you can find out more information. It'll be updated. So really, this is really our first early pass at Linux tracing tooling for WPA. The WPA tool is stable, but the plugins and SDK are basically beta quality, so they're pretty good. But basically, we have a lot of heuristics to be able to correlate, IO time and all this other things. We're not really Linux kernel experts, although there's other folks at Microsoft and the Cosine group that are. But these are our set of heuristics we've tried to use that work in some cases, not all the cases. But let us know if something is wrong or contribute when we make this open source. We'd love for the other scenarios and logs to work as well. So I mentioned already CPU sampling would be awesome to have, so you can actually see what's going on inside the program. And the new LTDNG is supporting these remote stacks soon, I believe. So we have great stack support in Windows, but we need to line it up in WPA, both for sampling, but just for any arbitrary, whether it's .NET or something else, would be great to have. Memory plugins would be awesome. Another thing is we have a technically called Windows WSL2 or Windows Subsystem for Linux, where basically you just it's our first shipping Linux distro Windows, and we'd love to be able LTTNG to run in there. So it's just a matter of having a kernel module available, and maybe some other plugins would be awesome to have as well. System D. So, do you want to add, Tristan?
Yeah, ultimately our goal is to make all the things that we've kind of built out to get the views going, open source. Long term, I would like to consider trying to make WPA itself open source and also cross-platform. Nothing to announce, but it's something that we have on the back of our minds, and it's something we want to kind of try to bring in, or try to help enlighten Trace Compass and try to bring in some of our concepts and our views into other existing projects. We're open. We want to make it that we can get the information out there and start kind of bringing in, because there's a lot of C# developers from Microsoft's perspective that are starting to write for Linux and for Mac, and we wanted to try to be able to support it, that we can bring more developers to more platforms.
So it is only for Windows right now, the UI?
Yes, questions and answers.
Yes.
Yeah, go ahead. Yeah, I can just talk about that. Yeah.
Yes.
Yeah, you can answer. It's for Windows only. Okay. Or that works too.
You can hear from the horse's mouth.
You hear from the horse's mouth.
Yeah, so the question, you mentioned that cross-platform, so it is only for Windows, the UI.
Yeah, the Windows Performance Analyzer was built on Windows Presentation Foundation, for example. So we have already actually done heavy, extensive work of the underlying libraries, except for the UI. Everything up to the UI itself, outside, like all that aggregation work, all the correlation stuff has already been moved to .NET Core. So we've already made a lot of the steps to make it cross-platform. The next heavy thing is to invest some time into making the UI cross-platform. We have some ideas. You know, we're kind of going back and forth on whether it makes sense to build what we see WPA as a cross-platform version, or help put some of that information back into other UI frameworks, or their either like Trace Compass or Thea.
But it wouldn't make more sense to, for example, work with Visual Studio Code as a UI, tool for, right?
Yeah.
Because
So
many of us are already using it. Like,
yeah, I casually hinted around it, partially because that is one of the things that we are thinking about. Yes.
By the way, it's a great.
Yeah. Thanks. Any other questions?
Yeah, so I'm wondering, all the various analyses that you showed today, I guess they were initially developed for Windows using TW events or some events from Windows Tracer?
So all the views that you saw today were completely based off LTTNG, except for the ones that are the specialized Linux logs, which are just ultimately text files. But a lot of the ideas for how we came up with those views came from inspiration from Windows perspective. Some have worked great, like the CPU history one is probably almost a one-to-one relation to what we actually show for Windows. But for other ones like process and thread, where branching is occurring, it doesn't really work well because Windows doesn't do that. So we kind of try to bring in some of that influence and try to kind of see if that approach would work. And then we learned that some cases it didn't, and we had to come up with something new.
Yeah, it wasn't clear. Like, yeah, 100% what you saw today is just Linux data. 100%.
Okay, so the I/O latency, for example, that we saw, you made it. It didn't exist before. You created it for these.
Yeah, so when we open source the plugins and make it programmatically available, for example, it'll do the calculation. You can consume it in .NET on Linux. For example, I/O time. That's not a secret calculation. We actually have slides that have some of the current heuristics that we have in the slides. Also, you'll be able to see it when it open sources. But like I/O time is super simple. You just, if you can, calculate the between insert and complete, for example. And then graphing it is another story, but you probably could do that in other frameworks as well. And so there's probably, again, we drew inspiration from what's available on Windows and said, hey, we want that as well. We want that view, it's very useful. But all the data was 100% Linux, and And even some other things we want, like, hey, arguments to exec-v or some program or sampling stuff are like just this far away, in my opinion, from having on Linux as well. Second question? Sorry. Yeah.
And also how do you ingest the CTF data? Did you write your own parser, or I'm really curious about this.
Very good question. Yeah, we built a purely C# parser. Didn't want to build another parser. Actually, we originally were going to use Babel Trace 2.0. Problem is it works great for running on Linux and works great for great for running on Linux. Worked on Mac too. We had some issues with it, but for the one is to be able to use it for WPA, which runs on Windows, we had some issues building in Windows, which has been fixed. I've been told that's now been fixed.
We now have CI on Windows, so
yeah. So we built it using Untitled. We actually built out the spec and actually code gen everything. That's going to be checked into. We'll put that out and open source it. Long term, yeah, I'd rather I'd rather have it just integrate directly with Babel Trace 2.0. That we're not. Again, someone else maintaining another CTF parser that's out there. Yeah, we're open to changing it up.
I wasn't hinting at that, but that's a good idea.
It makes sense.
Any other questions?
So all the traces are in the Linux machine, so they are in the guest. How does the Windows host get access to these traces? How are they consumed?
Yeah, I mean, it'd be a similar process on Windows. It's captured locally, and you just copy it with SFTP or something like that. So it's CTF format as a directory, index and binary storage. So you can either tar zip it up or just copy the whole directory. And basically, I think the offline support in CTF works pretty well, except for sampling. If you do the perf to CPU, it doesn't seem to work. Both also in Trace Compass as well, but it's just a simple copy. We also have for Windows ecosystem that's built on top of ETW and WPA, like distributed trace collection, that sort of stuff. If you want to do scale stuff, which is thankfully why I think system type of analysis is great. So like, hey, there's some perf problem on some server and quickly capture it. It could be anywhere from capture 500 milliseconds of data or capture 2 minutes of data, but being able to analyze it offline programmatically at scale, I'm talking hundreds of thousands of traces, and you can, whether it's in labs or whatnot, is pretty key. And we want this to be able for customers to use this, right? Same with Windows, right? WPA is used by our support and customers, and the reason why there's a community is because we want to see what's going on in the system. So we want the same thing for this tool. People peer what's going on inside Linux as well. All right, does that answer your question?
Yeah, thank you.
So I have one question about this tool. In my mind, that this tool is tightly coupled with Windows Server or this like Windows OS. Now you are using it for Linux, and so they have different kernels and different OS designs. So how do you converge the architecture?
Well, the great thing is you don't really want to convert it. So all these views you have, really they're graphing concepts and grouping concepts and all this stuff. So actually there was, besides the SDK to open it up to beyond the ETW, which Tristan can talk more about, all these concepts apply really well. You can graph anything, any kind of data. So the only thing that really you need to do is be able to parse in CTF. And yes, there's some concepts that are different at the OS level as far as between Linux. But really, yes, you're right. It's been associated WPA with ETW. And if we don't change the name, it still will be. But we didn't. Besides the SDK, you didn't have to make any graphing changes or anything. Is that right?
Yeah. To give you a little bit of background, WPA actually was originally designed to consume every single file format. Originally, it was built on the Windows platform, but the underlying engine, the Chrome itself, is purely built on Windows. But the entire underlying data engine and everything outside of the SDK is actually built on a cross-platform. It's just that with what we had for the resourcing available, we wanted to get up and running for Windows developers inside Microsoft. And it was very easy for us to, most of the people, analysts inside Microsoft have a Windows box available with their Linux box, that it was quickly able to get them to get these views. Some folks do use Trace Compass, and it's been very useful to be able to help figure out things. And that's one of the reasons why we actually made that new framework, is that we can actually be able to say, hey, we've had this data coming, whether it's coming from ETL. So it could go the other way around too. Well, today we are showing you the data for LTTNG. We are building the version that actually shows all the ETW information using the same exact framework. So it could be the flip. We could actually start showing ETW information into other frameworks like Trace Compass. So this way you could do like a kind of a host VM correlation if you actually had something going from ETW and something coming from LTTNG to actually get this holistic view.
Okay, thank you.
All right, any other questions? We have time.
Feel free, you guys are like, you're at Microsoft, you're here.
All right, thank you very much for the talk.